Welcome to the wonderful world of physics. This is a continuation of chapter 19 on the second law of thermodynamics. And in this video, we're going to look at section 19.4, entropy and energy quality. The second law of thermodynamics, the Kelvin-Planck statement, is it is impossible to convert thermal energy entirely to work. And that's a statement that we've seen in a previous lecture, which means that the amount of thermal energy or the amount of heat cannot be equal to the amount of work that's produced. But rather, as we saw with heat engines, the amount of heat drawn from a hot temperature source is going to equal the amount of work produced, but there must necessarily be an amount of heat that is wasted, and that's Q sub C. It's exhausted into the cold temperature reservoir, and oftentimes practically that's the environment. We've seen this example of going from order to disorder, where if you have a cup of hot water and a cup of cold water, one's at temperature sub H and the other temperature sub C, and you mix them together, there is less order than there was before. You have medium temperature water. The result is that there's less organization, there's less ability to do mechanical work. Now, what do I mean by that? As long as you have that hot water or the hot substance isolated, it could potentially be used as the hot temperature reservoir in a heat engine. And it could be used to produce work as long as the environment, the ambient temperature, is just cooler than it. Let's say the hot water in this example is 100 degrees Celsius. Well, you could get work from a heat engine where the cold temperature reservoir is 90 degrees, 80 degrees, 70 degrees, just something that's cooler than that. But now if you mix them, you have less ability to produce work. You've got medium temperature water, and maybe, for example, it's only 50 degrees. Well, it's still warmer than, say, the outside air temperature. Maybe the air temperature is 30 degrees, but it can't be used as a hot temperature reservoir over a cold temperature reservoir that might be 90, 80, or 70. So it can still be used to get mechanical work, but there's less ability to get it. However, keep in mind there is the same amount of energy. Conservation of energy does still occur. If you mix the hot and cold, you've got the same amount of energy. And yet there's a lower quality of the energy. There's less ability, as the second bullet point says, to do mechanical work. This brings us to the concept of entropy. Entropy quantifies the loss of quality or usefulness associated with an energy transformation. As a general rule, entropy increases during any thermodynamic process. Therefore, the amount of useful, usable energy decreases. So again, the example of the hot water and cold water, you mix them together. There you have an energy transformation, you have a thermodynamic process, and the amount of useful, usable energy decreases, and entropy increases. So entropy also brings up the idea that things go generally from order to disorder, as we saw with the example of the water being. I want to take a side trip here and think about something that doesn't at first seem to have anything to do with thermodynamics and heat, and to talk about order and disorder, organization and disorganization. And by the end of the lecture, I will tie it into what this has to do with thermodynamics. The idea of entropy also relates to this. Imagine that we flip two coins. And as we flip those two coins, we expect one of three results. In the left-hand column, you can see there, gives the results or the macro states. We can either get two heads, a head and a tail, or two tails. Now, the ways in which those turn up are the microstates. There's only one microstate of getting two heads, and that is, imagine we have a coin on the left and a coin on the right. The coin on the left is a head, the coin on the right is a head, so we'll call that head-head. But to get a head and a tail, there are two microstates. It can be head-tail or tail-head. And there's only one way to get two tails, and that's the microstate tail-tail. So if we count up how many microstates there are for each macrostate, to get two heads, there was one way of it occurring. To get a head and a tail, there were two ways of it occurring. And to get two tails, there was only one way of it occurring. So we go over to the fourth column, the probability of each macrostate. There's a 1/4, 25% probability of getting two heads. But there's a 2/4, or 1/2, 50% probability that we would get a head and a tail. And there's only a 25% or 1/4 ability to get two tails. Let's expand this experiment a bit and think about flipping 3 coins. If we flip 3 coins, you can see the possible macro states. We can either get 3 heads, 2 heads and a tail, one head and 2 tails, or 3 tails. You look in the second column of the possible microstates, how that could have occurred. Now, to get 3 heads, the only way to do that is to get head, head, head. So we can imagine we flip a coin on the left, a coin in the middle, and a coin on the right, and they all must turn up heads. But to get 2 heads and 1 tail, there are 3 ways it could occur. Head, head, tail, head, or tail, head, head. And you can see the rest of the macrostates. So you look over at the third column, the number of microstates for each macrostate, 1, 3, 3, 1. You look at the probabilities, and what you see is that it is more unlikely for all the coins to be the same than for them to be mixed up. So as we talk about order and disorder, you can think of it this way. It is more likely that the coins will be mixed up in some way than to all say the same thing. Now, let's consider a simple system, a box with 2 molecules in it. And in this box, there's a left-hand side and a right-hand side. And mathematically, this is going to relate to flipping coins. And I want to think about, where are the molecules in the box? At any one given time, where might those molecules be? And I'm just dividing this between the left-hand side and the right-hand side. In my picture, I've colored them a blue molecule and a red molecule. So one possibility is that both molecules are on the same side. So 2 on the left, 0 on the right. Another possibility, another macro state, is that there's 1 on either side. And there are actually 2 microstates for that. The blue is on the left and the red is on the right, and the red is on the left and the blue is on the right. 2 possible ways that can occur. And I've drawn this incorrectly. Sorry. Okay, I've just corrected with my pen the right-hand box, and now we see the 2 molecules, both of them on the right-hand side. So 0 are on the left side and 2 are on the right-hand side. The probability of there being an even distribution of these 2 molecules, meaning 1 on the left side, 1 on the right, is the highest probability. It's less likely that they are ordered all together on the left or all together on the right. Now let's consider a box with 3 molecules. You can see the microstates, you can see the various macrostates. So the first macrostate, that all of the molecules, all 3 of them are on the left-hand side. There's only one way for it to occur, and there it is, with a 1/8 probability. For there to be 1 molecule on the left and 2 on the right, there's 3 different ways it can happen. The red on the left, and that looks like a green and a blue on the right, or the blue on the left and the red and the green on the right, etc. For there to be 2 on the left and 1 on the right, you can see this third column. There's 3 ways that can happen. And then for all of them to be on the right, there's only one way. And these probabilities are matching the table of probabilities I showed earlier with coin tosses. But what we can see is that it is most probable that the molecules will be somewhat evenly distributed rather than all crammed to one side or all crammed to the other side. There is a low probability that all molecules will be confined to one side of the box. And the more molecules we have in this box, the more this picture builds and develops so that it is much more highly likely that the molecules are evenly distributed. So that if we consider a box with 100 molecules in it, now there's too many diagrams for me to draw, but if n equals 100, then what we have is 2 to the 100th power possible microstates. Now that is about 1.3 times 10 to the 30th possible microstates and 101 macrostates. The probability that all the molecules will be on one side of the box, all of them to the left and then none of them to the right, is 1 over 1.3 times 10 to the 30th, which essentially is 0. So it is highly unlikely that there's such order, such organization in the molecules that they'll all be crammed to one side. So we can see a graph, the number of molecules on the left side of the box and the probability. And so there's a distribution of how many molecules are on the left side of the box. Pretty close to 0, probability that 0 on the left side. Pretty close to 0 that 100 will all be on the left side. And it's distributed evenly so that it is most likely of any given macrostate that 50 of them will be on the left and 50 on the right. Now, boxes seldom have 1 molecule, 2 molecules, or 3 molecules, or even 100 molecules. Typically, when we talk about an amount of gas, we might be talking about trillions of molecules. So for about a mole, about 10 to the 23rd molecules, there's even less distribution. And so here we see the probability that the number of molecules that will be, if there's 10 to the 23rd in the box, the number of molecules at any given moment that are going to be on the left-hand side is going to be pretty close to 5 times 10 to the 22nd. And you see that sharp spike in the probability curve. It's not going to deviate too much from that. Anything other than near equal distribution is impossible. And so an application of this is the air that's in the room that you're in right now. Generally speaking, the air pressure on the left side, you can assume, is going to be the same as the air pressure on the right. Now, ventilation might mess with that a little bit, but as a general rule, we can figure the air pressure anywhere on one side of the room is going to be the same as the air pressure on the other, because the molecules at all times are going to be pretty evenly distributed. It is in theory possible that all of the air molecules could bunch up on one side, but it is so close to 0 probability. Even on my previous slide, I showed just with 100 molecules, it is so unlikely that we consider it essentially 0 probability that all the molecules would bunch to one side. For moles of air, it's even less likely. Okay, so let's bring this back to talk of entropy. Entropy relates to disorder in general, not just to heat flow. Systems naturally evolve toward higher entropy states, meaning higher disorder. So if you take coins or dice and you toss coins or dice, they will naturally evolve when you toss them to less order. Molecules in a box, just the same. Regions of different temperature. So if you imagine with the cup of hot water, the cup of cold water, if that water mixes, the hot region and the cold region aren't going to stay hot and cold very long. They will mix. That's the way the universe goes. So another statement of the second law of thermodynamics is the entropy of a closed system can never decrease. It will always stay the same or increase. Now, when you hear the word entropy, you can also think of disorder. This means that the entropy of the universe can never decrease. The order of the universe, or the disorder of the universe, is always increasing. And we see in cosmology that the universe is going from a state of order to a state of disorder. And everything around us goes towards states of disorder. Let's now look at some pretty simple, straightforward quantitative analysis of entropy, how we can actually calculate it and assess it. So entropy, we're going to use the capital letter S to represent entropy, is a function of the state of a system, just like temperature, volume, and pressure. And we're actually not going to be calculating entropy so much as change in entropy. And that's really what practically is more useful, not the entropy, but how much in a thermodynamic process the entropy changes. And change in entropy, delta S, is equal to the integral of dq over T. Now you know that Q has to do with heat and temperature, or T is the temperature. I'm going to, for now, use the simplified equation that delta S is just simply Q over T. And we'll see the limitations of this simplification, and later on we'll see using the calculus equation. So, but for as long as temperature doesn't change, we can use just Q over T. So let's do this example. An ice cube that's at 56 grams, or it has a mass of 56 grams, it's at 0 degrees Celsius, is allowed to melt. And after a few minutes, half of the mass is now liquid water at 0 degrees Celsius. Compute the change in entropy. Well, if temperature doesn't change, we don't have to use the calculus. We can just say change in entropy is Q over T. Well, we need the Q, and we've just seen that 28 grams is melting. So Q equals mass times the latent heat of fusion, 0.028 kilograms times 334 kilojoules per kilogram. And we get that the heat that went into it is 9.352 kilojoules. So the change in entropy is Q over T. We're going to divide by, you can't divide by 0. And 0 is Celsius degrees, so you need Kelvin, 273. And what we get is that the ice has had, for the ice, a change in entropy of plus 34 kilojoules. Now that's not for the closed system, because remember there was heat that was allowed to flow into it, so heat came from some external source. But at least for the ice, you can see just this basic calculation of how we do entropy. Now let's do a closed system. Let's say that we have 50 kilograms of water at 20 degrees Celsius, and we mix it with 50 kilograms of water at 24 degrees Celsius. And we're going to estimate the change in entropy, and as usual, we're going to assume this is a closed system, no heat flows in or out of the environment. Now, we have to think the final temperature. Well, I've kept this example simple enough that you can see if it's equal masses of water, the same substance, one's at 20, the other's at 24, the final temperature, we don't have to hopefully do a calculation for that. We can just see they're going to meet in the middle at 20 degrees Celsius. That is relevant to this problem. So let's calculate for the cold water. How much heat went into the cold water? Q sub 1. It's mc delta T. So 50 kilograms times 4184 joules per kilogram Kelvin times the change in temperature. And this is where the final equilibrium temperature is necessary to use. 22 degrees minus the original 20 degrees. And so what we get is the heat that went into the cold water is 4.184 times 10 to the 5th joules. So its change in entropy is Q over T. Now in the previous example with the ice melting, the ice was at 0 degrees Celsius or 273. But what do we take the temperature here? The cold water at one point was 20 degrees Celsius, but it ended up at 22. So what do we do for temperature? Well, we're going to use the average temperature temperature as an estimate. So we'll use 21 degrees Celsius or 294 Kelvin. So we take Q1 over 294 and we get plus 1423 joules per Kelvin. You might want to pause the video for a moment and go back and look over and make sure you understand what I've done so far. All right, now we need to consider the entropy, the change in entropy of the warm water. So Q sub 2 is the heat that goes into the warm water. We expect this is going to be negative because we know that heat comes out of the warm water. And so Q sub 2 is mc delta T. We have the mass, the C, and then we figure the change in temperature is final minus initial. And up here we said the final temperature is going to be 22 minus the initial 24. So it has a change in temperature of -2 Celsius degrees. And we get a change in entropy, heat, Q sub 2, of -4.184 times 10 to the 5th joules. Now, that goes along with what we should have expected. The heat into the cold water was 4.184 times 10 to the 5th joules, and that's how much heat came out of the warm water. But we're going to get a slightly different quantity when we calculate entropy. The change in entropy for the warm water is Q sub 2 divided by, and this is a different temperature that we're divided by for the cold water, the temperature of the warm water. And again, we have to figure, what do we consider the temperature of the warm water? It started at 24, it ended at 22. Let's take the average temperature for the warm water, 23 degrees Celsius, which is 296 Kelvin. So we do the heat divided by that average temperature, and we get -1414 joules per Kelvin. You look at the two red boxes, the change in entropy of just the cold water, the change in entropy of just the warm water, and they are slightly different numbers. Well, for the closed system, we're going to add those changes in entropy. So the total change in entropy is the entropy change for the cold water, so delta S1, plus the entropy change for the warm water, delta S2, and it comes out positive. And this is one of the statements of the second law of thermodynamics. For a closed system, entropy will never decrease. At best, it will stay zero, but most often it will increase. You'll always have a change, a positive change in entropy. So in this case, plus 9.6 joules per Kelvin. So as this example shows, total entropy always increases. In the first entropy calculation example, where we had the 56 grams of ice melting, temperature stayed the same. And we could just simply use change in entropy equals Q over T. Very simple equation. And in the previous example, temperature didn't change by much. And so we just used the average temperature and said that's good enough. But we must use calculus if temperature changes considerably. Now, it is only from experience in doing such calculations that one is able to discern how much is a considerable change in temperature. But I want to show you this previous example, but I'll use calculus and show you, it'll be a good demonstration of how we use the calculus, the full entropy change equation, and you'll be able to see that in this case it was okay just to use the average. So here we have the same problem as the previous one, 50 kilograms of water at 20 degrees Celsius, and there I've already converted it to 293 Kelvin. 50 kilograms of water at 24 degrees Celsius, and there I've called it 297 Kelvin. And we want to know the change in entropy of 1, which is the cold water, change in entropy of 2, which is the warm water, and then the total change in entropy. So for the cold water, now I'm going to use the calculus equation. Change in entropy is integral of dq over t. We're going to take the integral, and we actually want to integrate with the variable being dt. So we want to integrate over the range of temperatures. So the limits of integration are going to be T1, the original temperature, and T, the equilibrium, the final temperature. And dq, what I'm doing here in the numerator, comes from Q equals mc delta T, Well, for that a small increment of heat added, we're going to call that mc dt. Instead of mc delta t, it's mc dt. We can throw the mc to the left, and then we're taking the integral of dt over t. Now, taking the integral of dt over t, that becomes the natural log of t. So here we have the change in entropy of 1 is mc times the natural log of t from t1 to t. And taking the difference, natural log of t minus natural log of t1 by our rules of logarithms, that is the natural log of t over t1. And so what we have is, well, before I go on to the next line, let's see, what is that final t? Well, remember, final t is going to be the average of the cold water and the warm water. Now, that is only specific to this example where it's equal masses and equal substances, but it works for this example nice and conveniently. So the final temperature is the average of T1 plus T2. So here, that's what I've substituted in here into this fraction for T. And again, keep in mind, that only worked, that simple equation that I did in the light blue and the cyan color, it only worked because they were equal masses. And so as we calculate this, we plug in the values. Delta S1 is 50 kilograms times 4184 joules per kilogram Kelvin. Times, and we plug in the values and we get 0.0068027, which, by the way, happens to be roughly the change in temperature over the average temperature. And so what we get is plus 1423.13 joules per Kelvin. Now, the reason I say in the red, this happens to be roughly delta T over the average temperature is because if you look back how I did this example, but just doing mc delta T over average temperature, there it is, mc times delta T over average temperature. So it's very, very close when you do this calculation. Now, we can do the same thing for the warm water. Delta S2 is mc times the natural logarithm, but what we're going to have here instead of T1 on the bottom, because we integrated T over, instead of T1, now it's T over T2. So this becomes T1 plus T2 over 2T2. And that becomes negative 1413. And I wrote in such small print, I'm sorry, I think that says a 0.52. I can barely read that, joules per Kelvin. So what we get when we add those is a change in entropy of plus 9.6 joules per Kelvin. Now that is the same result as we got before with the non-calculus version, but only because temperature was nearly constant. So in this example, where temperature difference was only 4 degrees and the temperatures only changed by 2 degrees, it was just easier not to use calculus. As I conclude this section in this chapter, I want to bring the discussion of entropy back to heat and thermodynamics. Earlier in this lecture, I talked about hot water and cold water, and that there is a quality, there's a usefulness in the hot water in that it could be used to run a heat engine. It's a higher temperature than what a cold temperature reservoir might be, and we could get useful work out of it. But as soon as we mix it with the cold water, it's medium temperature, and we have less ability to use it to run a heat engine. There's less usefulness to it. I want to give you another example, and this example I learned from a book called Maxwell's Demon, and it's about James Clerk Maxwell, who imagined that there is, well, he imagined a box such as you see there. And by the way, the book Maxwell's Demon, it was written by a professor of mine, a physics professor, Dr. Hans Christian von Baer at the College of William and Mary. And he wrote about what James Clerk Maxwell imagined. So imagine this box. And earlier in this lecture, I talked about a box with various numbers of molecules. Well, let's talk about now this box, and it could have even numbers of molecules. Doesn't really matter what number of molecules on each side, but the temperatures of each molecule. Because remember, each molecule has different kinetic energy. At any given moment, as they're going in random directions at random speeds, some are going fast, some are going slow. And so here I've drawn this box with a divider in between. And they're at equal temperatures, as a box would tend to be, same temperatures. And at any given moment, as I said, some molecules are going fast, some are going slow. And Maxwell was wondering, is there a way to separate the hot from the cold? And he imagined, what if there was a doorway in between in this divider, and there was a sentient being that he called a demon, and we can imagine there's a little elf right there in between. And as hot molecules, or what I really mean is fast molecules, molecules with high kinetic energy, as they pass by him on the left, he grabs one and he throws it to the right. And maybe as the slower molecules on the right pass by him, he grabs one and throws it to the left. So that this demon is making a discernment of the molecules, and he is able to grab the fast ones on the left and throw them to the right, and maybe grab the slow ones on the right and throw them to the left, so that eventually he has divided the cold on one side and the hot on the other side. And he seems to have violated some laws of thermodynamics, gotten this separation of cold and hot. Now, we do not exactly the same thing, but you think this is what we want to accomplish with a refrigerator. We want to get cold. We have a cold interior of a refrigerator, and we want to make it maybe even colder. And we want to take the heat and throw it to the outside. But this fictitious demon here wants to separate these things. And is it possible to get this separation where we get order from disorder, where we get the hot on one side and the cold on the other side? And that would mean that in the box that there is a decrease in entropy. The change in entropy would be less than zero. But as Maxwell was contemplating this, what he realized was that necessarily there is the demon who has a change in entropy that is increasing. Because in order for this being to separate the hot and cold, he has to be thinking, he has to use muscles, he has to be doing some work to make this happen. And in the foods that he ingests and metabolizes, there is overall an increase in entropy in his body, which is going to be more than the decrease in entropy that he caused by this disorder to order, by the organization of the molecules. So in the end, Maxwell concluded that if you take the change in entropy in the box and the change in entropy of the demon, they necessarily must be greater than zero. Entropy in this closed system must increase. This is the end of chapter 19, and particularly section 4, entropy and energy quality. Have a great day.